Hello everyone, I'm Yue Chen from University College London. The topic of my report today is intermediate features are not useful for tone perception. As we know, how listeners perceive speech is still a mystery. It's widely assumed that multiple acoustic cues are needed for perception. For example, formants are the primary cues for vowels. Pitch and duration are useful for lexical tones, etc. But how exactly those cues are used to achieve the recognition of phonetic categories from continuous speech is not clear. There are many theories about speech perception, but most of them assume that listeners first extract features or properties before identifying the sound category. This view goes back to the classic theory of distinctive features, which attempts to economize the representation of phoneme categories by minimizing the number of acoustic properties needed to classify segments. Consistent with the feature theory, a widely accepted idea is that feature or cue extraction is a key to speech perception. The auditory theory assumes that it is auditory properties of phonetic events that listeners tend to. The motor theory assumes that speech perception is achieved with an articulatory recognition phase before the identification of words. An exception is the exemplar models postulate that whole-size exemplars are stored. However, they do not specify how exactly perception is achieved. The distinctive feature theory, auditory theory, motor theory, as well as many other conceptual frameworks of speech perception, share in common what we will refer to as the feature-to-perception hypothesis. They all claim that an intermediate phase, feature extraction, is needed in perception. However, none of them specifies how exactly features are extracted and how exactly the features are turned into perceptual categories. What has really been theoretically explored is whether it is possible for listeners to process the speech signal as a whole without extracting any intermediate features. In this study, we wanted to test these two hypotheses on tone recognition to see tonal feature or F0 contour, which is a real categorical unit. Well, tone is a multi-cues related phonetic event, but previous research has shown that fully continuous F0 contours are sufficient for the categorization of the four Mandarin tones produced in connected speech. So here, we just use F0 contours to test the direct category perception hypothesis. For the tone recognition, we use SVM model to do the classification. As mentioned before, F0 contours are sufficient for tone categorization. So here we use F0 contours to represent the whole signal in tone recognition. For tonal features, we reduce the resolution of F0 to simulate the feature reduction. Now I'm going to introduce why we did it this way. There are four main tones in Mandarin tone system. We don't discuss neutral tone here. In the figure 1, we can see the F0 contours of four Mandarin tones for male and female speakers. Derived from distinctive feature theory, binary tone features were introduced by Wang Shiyuan. In this system, all tones can be represented by high and low. Tone 1 is high-high, tone 2 is high-low, tone 3 is low-low, tone 4 is low-high. A more broadly accepted practice is use a 5-level system proposed by Zhao Yuanren. This system assumes that only 5 discrete levels are needed to distinguish all tones of a language. The 4 lexical tones of Mandarin are represented as 5-5 for tone 1, 3-5 for tone 2, 2-1-4 for tone 3, and 5-1 for tone 4, where a larger number indicates a higher pitch. Under those assumptions, It indicates that to perceive a tone, listeners have to first determine which pitch level it is at each temporal location. For example, you have to first determine if it is high-high or high-low or other patterns before determine which tone it is. In such a tone recognition process, the key is to first detect two discrete scales with two temporal specifications and five frequency specifications. Following this scheme, the temporal resolution can be reduced to 2 points per tone, and the frequency resolution can be reduced to 5 or even 2 levels per tone. The reduction of temporal resolution was done by extracting a varying number of equidistant points along the F0 contours. The reduction of frequency resolution was done by fitting the F0 points into different numbers of fixed bands. Figure 2 shows some choices of resolution reduction on a tone 3 F0 contour. For all reduced temporal resolutions, linear interpolations were applied to link up adjacent points. In this study, the data were syllable-sized F0 contours produced by 4 female and 4 male Mandarin speakers. Each stimulus corresponds to a syllable in a disyllabic mama produced in a carrier sentence with either high or low pre-F0 value and post-F0 value. Each token is a 30 equidistant time-normalized discrete points vector. There are a total of 1,408 tokens of tone 1, tone 2, and tone 4, 1,232 tokens of tone 3. The number of the tokens were fewer for tone 3 because we removed standing tones. The whole dataset was then divided into a training subset and a testing subset with a ratio of 2 to 1. The experiment used F0 contours of the 4 Mandarin tones with full resolution to train a SVM model, which was then used to classify the tonal categories of contours with varying levels of resolution reduction, as shown in Table 1. We set up 3 experimental conditions, all with full resolution as a reference condition. One is reduced temporal resolution alone. Then reduce the frequency resolution alone. The third one is reduce both resolution together. Here comes the result. As shown in Figure 3, at full resolution, the error rate was low at 2.6% for contours in semitones and 60% for contours in hertz. The lower rate of contours in hertz is unsurprising, as a logarithmic conversion in calculating semitones has effectively normalized the vertical span of the pitch range, with only individual difference in pitch height still retained. As temporal resolution reduces, the rate of tone recognition remains high until there are only 2 temporal points left. When we reduce frequency resolution, as shown here, tone recognition rate is more sensitive to reduction in frequency resolution than to temporal resolution. It starts to drop at 40 bands, and the decline is faster for contours in hertz than those in semitones. By 5 bands, the recognition rate have dropped below 40% on both scales. As shown here, when temporal resolution and frequency resolution were reduced at the same time, only the effect of frequency resolution can be clearly seen, as the recognition rates are largely the same across different temporal resolution except for the 2 points condition, which started low even with full frequency resolution. The only difference between the two figures are that a major drop occurred between 37 and 18 bands for contours in hertz, while a major drop occurred later between 18 and 9 bands for contours in semitones. And the rate is overall lower for the hertz scale than the semitone scale. We can see from the experimental result at full data resolution, F0 contours both in hertz and in semitones can achieve high tone recognition rate. and the rates are similar to tone confusion metrics based on human perception experiments. It shows that, to some extent, the SVM model on F0 could show the patterns of human perception. Also, the high recognition rates show that, despite the variability, tones produced in context by speakers of both genders still have enough in common to allow a pattern recognition algorithm to accurately recognize the tonal categories. When we reduced the resolution, no benefits were seen in terms of improved tone recognition rate. Instead, with reduced temporal resolution, the performance did not change much till the number of F0 points were reduced to 2, when the recognition rate were dropped to around 50% for F0 controls in Hertz and 65% for F0 controls in semitones. Interestingly, 2 pitch location per tone is exactly what is assumed by the widely accepted feature representation of Mandarin tones. With reduced frequency resolution, tone recognition rate dropped quickly. The decline was already apparent from the full resolution to around 40 frequency bands. Then a significant drop to below 50% occurred by 18 bands for the Hertz scale and 9 bands for the semitone scale. For both scales, the recognition rates are already at a level that no Siri would consider as viable. When there are only 5 frequency bands, the recognition rate were both below 40%. As shown in present study that tone recognition can be achieved at a high accuracy without speaker normalization as long as full resolution of the raw data is retained. Why should there still be a need to extract features? So, no intermediate steps are needed to first extract economical tonal features before recognizing the tones. In conclusion, syllable-sized continuous F0 contours with full resolution can be used to train an SVM model to achieve high tone recognition rates without extracting intermediate features. Reducing resolution from the F0 contours will result in reduced rates of tone recognition. These findings pose serious questions about what we call the feature-to-perception assumptions. As an alternative, we would like to suggest that raw acoustic signals can be processed directly to recognize phonetic categories without explicitly extracting intermediate features. Observation of the role of certain features is useful only for descriptive purpose. In next step, we would like to build a feature detector for Mandarin tones to further test the usefulness of processing features in speech perception. That's all for today's report. Thank you.